All right, so the first two lectures will be relatively elementary for the experts, but I think I can't expect everyone to know about this. So I'll do it, and it'll mostly be the bare bones things we'll need to even write down what the Yang-Mills equations are. In the notes that I'll post after the lecture, there will be a decent amount of exercises that either you already know how to do, or if you haven't done, you should do once in your life if you want to look at these things. And then lecture 3 onward, things will get a bit sketchy and hand wavy if I want to cover as much as I want in this week. So there will be less proofs, and the proofs that do exist might be less rigorous. But hopefully I can get the big idea across in the last few lectures. Okay, so let's just get right into it. So principal bundles. I should say principal G bundles. So for the remainder of today, we're going to fix a closed. So this means compact and boundaryless manifold X, smooth manifold X, and a Lie group G. So we have a definition, a principal G bundle. Someone posted something in the Slack. Okay. A principal G bundle over X is a fiber bundle. So it's a map pi from E to X, or I should call this P. Equipped with a smooth right G action. So the convention is for principal bundles is the G action is on the right. And then I'll use this notation here to show that it's acting on the right. So satisfying some properties. So one, the G action preserves the fibers of pi. So I'm going to denote that P sub X to be pi inverse of X. And the restricted action of G on this fiber is free and transitive. So in other words, the fibers of the map pi are G torsors. So a G torsor is just a space with the free and transitive action of G. So 2, for any point X in X, there exists a neighborhood U containing X and a G equivariant diffeomorphism phi from pi inverse of U to U cross G. So the right action on here is by right multiplication on the second factor, such that this diagram commutes. So this map phi is called a local trivialization. And then this map here is a projection onto the first factor. All right, so that's what a principal G bundle is. So here's an example. This should be the main example you have in mind when you think about them. So let's say let E to X be rank K real vector bundle. And then for a point X and X, let this B sub X be the set of linear isomorphisms from Rk to the fiber E sub X. So B is an iso. So we have an action of GLKR on here by precomposition. And this is free intransitive. So this is, and the action is free intransitive. So B sub X is a GLKR torsor. And then we define what I'm going to call B GLKR of E as a set. It's going to be the disjoint union over all points in X of these B sub X. So using local trivializations, of E, we can.
Hey Jeffrey, somebody in chat said that like maybe when you write, try to write on the bottom a little bit, or like
oh yeah,
people can see
the
rest when you write. But
yeah. Thanks. I will also post these handwritten things at the end as well, I think. Though that might not be necessary if I post the other notes. I can do both. So using local trivializations, we can give the set a smooth manifold structure. Such that the natural map from this space to X is a principal GLKR bundle. So we're going to call this the let's say frame bundle or bundle of frames, something along those lines. Okay. So here's another example. Suppose we have our vector bundle above, E to X, also has a fiber metric. So this is some smoothly varying inner product on the fibers. Then we can let B O comma X be the set of maps from Rk to the fiber such that B is an isometry. So the inner product on Rk is the standard one, and then the inner product on Ex is the one you get from the fiber metric. And then in a similar fashion as we did as the previous example, we can take B sub O of E to be the disjoint union, and we can give it a topology and a smooth structure to make it a principal OK bundle. So we're going to call this the orthonormal frame bundle. Okay. Sorry. And then we can, the same works for complex vector bundles. And Hermitian metrics. So we'll just, in that case, replace GLKR with GLKC, and then OK gets replaced with UK, the unitary group. Okay. So here's a definition. So let P to X be a principal G bundle, and F a smooth manifold with a smooth right G action. The associated fiber bundle is the space. So it's denoted P crossover G with F. So it's the product mod some action of G, where it's the diagonal action. So P comma F dot G is defined to be P dot G, F dot G. So this comes with a projection. Oh, I guess I should name this map for P, so pi. So this comes with a projection from P crossover GF to X, where you take an equivalence class P comma F, and you map it to pi of P. Okay, so here's a proposition. Or I guess it's more of an exercise because I'm not going to prove it. Use local trivializations of P to show that the associated fiber bundle is a fiber bundle with model fiber F. And then to relate this to what we said before, here's another exercise. Let E to X be a vector bundle. Show that the associated fiber bundle B GLKR of E crossover GLKR and RK using the standard action of GLKR and RK. Just show that this is isomorphic to E as a vector bundle. So I guess maybe part one and part two is if E has a fiber metric, so this should be the same proof as for part one, but the question is, how do you recover the fiber metric? Okay. So this tells you that, so like going from a vector bundle to its principal bundle of frames, and then you can also recover the vector bundle from the principal bundle by taking an associated bundle with a linear representation. There's something I meant to write down, but I guess I didn't in my notes, so I'll mention it here. So maybe I'll add a third part. So if rho from GLKR to GLKR is the dual representation to the defining representation, so i.e. rho of A is equal to A inverse transpose. Show that the associated bundle you get using this action is isomorphic to the dual bundle to E. Okay, so moving on, another definition. So let E to X be a vector bundle. An E-valued differential K-form is a global section.
Hey,
yeah.
Jeffrey, it seems like the screen is kind of frozen.
Oh.
What does it say on your screen, I guess?
Let E to X be a vector bundle and E-value differential. I can stop and, oh, it paused. I see.
You paused at the exercise.
Yeah, I think I paused. Is it back?
Yeah, it's good. So maybe you should like just
okay.
Just a little bit. Oh, start from number 3. Yeah.
Right. Yeah, I'll just say, did it freeze at 2?
Yeah, it freeze right at the sentence. How do you recover the 5?
I see. Okay, so for the third one, so you let rho be the dual representation to the defining representation, which is just the identity map GLKR to GLKR. So in this case, the dual of that would be rho of A is the transpose of A inverse. So then the exercise is to show that the associated fiber bundle you get using this representation is the dual bundle to E. So if you think about, if you apply this to maybe like the tangent bundle, or E is the tangent bundle to X, maybe this will illuminate the differences between the tangent and cotangent bundle in terms of how things transform with respect to coordinate transformations. This is what helped me understand it, I think. Okay, so this is what I wrote after I accidentally paused everything. So you're taking a vector bundle E to X, and then we're defining an E-value differential K-form as a global section of, so the kth exterior power of the cotangent bundle of X, tensor E. So we're going to denote the space of E-valued K-forms as, I'm going to say, omega kx of E. And then if V is a fixed vector space, a v-valued k-form is an e-valued form for E being the trivial bundle X cross V. And then the space of v-valued forms will denote as omega sub k, omega superscript k sub x of v. So in a local frame, for E, we can write a k-form omega as omega I tensor E sub I. So I'm using the summation convention where if you see something repeat on the top and bottom, you sum over that index, where the omega I are in our k-forms. So this is the space of just differential k-forms on X. And the EI is the local frame. So it's notational convenience will usually omit the symbol, so we'll just write omega I EI. Okay, so we're going to need some operations on these e-valued forms. So suppose we have omega, a k-form valued in E, and eta, an L form valued in E. To find their wedge product, omega wedge eta in this local trivialization is going to be omega I wedge eta j EI tensor EJ. So this is going to be a K plus L form valued in the tensor product. So if you wedge together two e-valued forms, you don't get an e-valued form back, you get an e-tensor e-valued form back. So here's one operation we want to do, and here's the other one. This one's pretty natural, as we're extending the exterior derivative. So d omega is just defined to be d omega I ei. So you just apply exterior derivative to all the forms appearing in the expansion. Oh. Okay. I accidentally looked at the wrong side of the page, so I will insert another one. Sorry, I did things in a weird order. Okay, so sorry, forget I said that for a second. We're going back to associated bundles. So here's more examples. And these are going to be ones we'll need later. Sorry about this. So one, let G act on the right of G by G dot H is equal to H inverse GH. So conjugation by the inverse. So it's a right action. Then this bundle called add P is the associated bundle you form from using this G action. So this is a bundle of groups. So it's not a principal bundle. Each fiber is so it's not exactly a principal bundle, it's slightly different. But each fiber has the structure of a group. So 2. So I'm going to use script G for the algebra because I can't write mathfrak very well. The algebra. And then you have this action of G by the adjoint action. So I guess you'll be doing the adjoint action of the inverse of an element. So it's a right action again. Then this bundle is defined to be the associated bundle you take with the Lie algebra with this action. And then I really should have said this right after, but I looked on the wrong side. Sorry again. So this is maybe how you characterize sections of associated bundles as some sort of G equivariant objects. So if we let gamma x to E denote the space of global sections of a bundle E to X, and so then if E is equal to some sort of associated fiber bundle, we have a bijection between global sections of E with G equivariant maps from P to F. And then I guess the proof I think I left as an exercise as well. So I think the motto you want to think about here is for associated bundles, equivariant objects on P become regular objects on X valued in some sort of associated bundle, I think is the way you want to think about it. Okay, so now we can go back to vector bundle valued forms. Okay, so sorry about that. So we'll mostly be concerned with G-valued forms and GP-valued forms for our discussion. Okay, so if we're talking about G-valued forms, we get a few more operations. So let's talk about those right now. So if we fix a basis, so C sub I for this Lie algebra G, then this gives a global trivialization for the trivial bundle. X cross this Lie algebra. And any G-valued form omega can be written.
Jeffrey, can you hear?
Yeah.
Yeah. So one of the questions we had is, so the example 2 you gave about d omega.
Yes.
Right here. Yeah, d omega, that's not that like that's not invariant of the frame, right? Like implicitly you chose a framing. Basically you choose EI, the basis.
Right. So I was concerned about this for a second. So I think you're right in the sense that you need the transition functions of the bundle to know how these things transform, right?
Right. So maybe another way to put it is like, yeah. I mean, like,
But I think taking D of the forms is fine because,
I think that's not what the connection is. I mean, that's what you implicitly kind of did here, right? I mean, like so more explicitly, like you have a principal G bundle, whatever. Like when you pick the frame, you literally pick a trivialization, and then you take in the flat connection associated with trivialization to write down.
Right. That's D. That would work if it's a flat bundle.
Right. But that's implicit.
But this isn't necessarily a flat bundle. So this does depend on the choice of trivialization, which is concerning.
Right. Like I don't think this d omega like exists without trivialization. That's what I'm saying. Because implicitly you're saying that like if you just have DEI is flat, right? So I mean like defining a exterior derivative is the same like on a vector bundle is the same thing, or on vector value forms are the same thing as
a connection.
Right.
Okay, so my concern is usually when you do the like the curvature, it's like of a connection, it's like dA plus something, right?
Right.
But so like maybe you have to show that that D is independent of or the whole thing is independent of trivialization if you just do dA locally in a frame.
Right. And like in your example, so yeah, I mean like okay, so in your example, what implicitly that you wrote down here is when you take D of omega, which is omega I EI, then you're supposed to take the exterior derivative with omega I, but you're also supposed to take a derivative against EI. But implicitly you're written down here, D of EI is 0. So your Christoffel symbol, whatever, is all 0. Implicitly you're doing a flat.
Right. So but I mean a flat connection doesn't necessarily exist. So this wouldn't work in all times.
Right. And like maybe more importantly, like I think you like if you write it this way, that's not just an invariant thing of E. Like
right, because you need to keep track of the transition functions of the bundle E to know how this. I mean, that just means this isn't well defined in terms of you've explicitly fixed a frame to do this.
Right, exactly.
And then
this is not, yeah.
And you can only do this in a frame.
Yeah.
And like going between frames, this isn't a well defined thing. Right. But then, okay, if you want to continue this discussion, I do have a question now. So like, you know how you write the curvature of something is like dA plus like 1/2 AYJ or something, right?
Yeah.
So that dA is what I've written down, presumably.
I see what you mean. Yeah.
And then I guess you have to show that it doesn't depend on the choice of frame if you add together this correction term of 1/2 of AYJ.
Right, exactly. So I guess mathematically speaking, like you have to have the whole package. If you just write down dA,
it doesn't make sense.
Yeah. The covariant derivative, the entire thing makes sense. Then
right.
It's you wrote it down locally, but like the entire covariant derivative inherently makes sense from the data you choose after a connection, but the dA part itself does not make sense.
I see. Okay. So maybe I'll put here that this is local definition. Dependent on choice of frame. So this isn't really like a global definition, but something like a shorthand notation people use to define other quantities, maybe is the best way to say this. This does make sense for a trivial. Yeah, okay, yeah, like you said, for a flat bundle, this makes sense, but until then, it doesn't. Okay, thanks for bringing that up. Okay, so where were we? So we have a basis for a Lie algebra. So we have a global trivialization of the trivial bundle. So we can write omega as omega I xi sub I. So then if we have omega k form, oops, eta and L form, we define this bracket. So omega bracket of omega wedge eta as omega I wedge eta j, and then instead of tensoring them together, you take the bracket of the Lie algebra elements. So you can think of it as the composition of the wedge product with the bracket operation you get from the Lie algebra. Okay. So now, did I put everything in the wrong order? Okay. So let pi from p to x be a principal G bundle. So the kernel of d pi is a vector bundle. The map pi is a submersion. So the kernel is actually a vector bundle. There's no like weird dimension jumping that's occurring. And then we're going to call it V, living inside the tangent bundle of P, and then it's called the vertical distribution. So geometrically, the fiber of V over X is equal to the tangent space. What am I trying? No, sorry. Is equal to the tangent space at P of the fiber over pi of P. So if you think of the projection as going vertically, these are exactly the ones that get smashed down by the directions that get collapsed by pi. So if you think of the projection as going down, these are the vertical directions, so to speak, hence the name. So here's the definition. Connection on P is a distribution. So distribution is just some vector subbundle of the tangent bundle of P, such that, so it satisfies two properties. One, when you direct sum it with the vertical distribution, you get the whole tangent bundle of P back. And two, this is a sort of G invariance property. So you take the differential of the right action of G at P, and then you apply it to the fiber of H over P, and then you should get the fiber of H over P dot G. So H is also called the horizontal distribution. And then denote the space of connections. So this script AFP. So to relate these connections to vector bundle valued forms, we're going to have to make an identification of this vertical space with something in terms of the Lie algebra. So let X from G to G be the exponential map. So if you think of elements of G as left invariant vector fields, this is just following the flow for time one of that vector field from the identity. And then X be an element of this Lie algebra and P a point in P. Then we get a curve. So gamma sub X comma P in this principal bundle P, whose value at 0 is equal to P, where you define this to be P dot the action of the exponential of T times X. So this is the infinitesimal action of G. So since the action the fiber containing preserves the fiber containing P, the tangent vector. So in physics notation, we use the dot. So this is d dt as t is equal to t goes to 0 of this curve. So this is actually an element of the vertical space containing P, the vertical space over P. So since the action is free, this tangent vector is equal to 0 if and only if this Lie algebra element is equal to 0. Furthermore, this mapping taking X to this tangent vector is linear. So by a dimension count, this is an isomorphism from this Lie algebra to this vertical space at P. So doing this over all P gives an isomorphism from this trivial bundle. So I'll just denote with the underline, but this is X cross G, and this is isomorphic to the not X, P cross G with the vertical distribution V. So implicitly, we'll identify Lie algebra elements with vector fields on P, with the vertical vector fields on P induced by the infinitesimal action. So it's going to be these tangent vectors varying over all points P in the principal bundle. Okay, so it's a proposition. So for X and G, x tilde be the vertical vector field. Induced by x. And then for G and G, we have so this is right translation by G, and you take the push forward, so the differential. It's equal to the adjoint action. It's equal to the vector field induced by the adjoint of G inverse applied to X, adjoint action of G inverse applied to X. So for the proof, I will be posting notes, the computations there. Or you can do it yourself if you want an exercise. And so this should be similar to a thing we said about characterizing sections of associated bundles. So P to X be a principal bundle. And E equal to P crossover G with W and associated vector bundle. Coming from a linear representation.
Hi, Jeffrey. Sorry to interrupt, but a question was asked, where would you put up the notes?
I'll post them in the Slack channel.
Okay, thanks.
Also, if you have any questions, you can either post them in the Slack channel or direct message me on Slack. I don't think I forgot to mention this beginning, but right. I technically have a TA, Arun, but I promised him he shouldn't have to do anything, so please direct all questions to me. Also, Arun, I think, is sick right now, so yeah. Right, so we have an associate bundle coming from a linear representation, rho taking G to GLW. Then there is a bijection. Wow. Okay. Between E-valued form. I think I wrote my notes in like a really bad order. I apologize for how disorganized things seem. Right. Okay, so there's a bijection between E-valued K forms on X and K-valued P form, and W-valued K forms on P satisfying some conditions. So this is the conditions. So the pullback of alpha by the right action of G is equal to rho of G inverse applied to A. And then also the interior multiplication of X into alpha is 0. So alpha vanishes in all vertical directions. So this should really be the same idea as G equivariant objects on P descend to regular objects in X for some associated bundle. And I think the proof I left as an exercise. And again, I'll be posting the notes with the exercises in the Slack channel. Okay, I'll say one more thing and I think we can just stop because I think my time is running out. So suppose we have a horizontal distribution H inside of TP. So the direct sum decomposition gives a projection map from TP to V. So remember that this is also equal to the trivial bundle P cross G, or isomorphic to, with kernel H. So this allows us to interpret H as an element A inside of the algebra valued one forms on P, called the connection one form. So proposition A satisfies 1, so it's pullback under right translation. We'll add G inverse of A, and 2, the interior multiplication by X. So in this case, it's a one form, so you just put X into A, and then you get X back. So this identifies the space A sub P as a subset of Lie algebra valued one forms as P. Right, I think I'm out of time. And I think this is probably the best stopping point I can get to. So I guess I'll just open it up to questions, or you can just leave if you want.
Could you say a bit more about how you get this one form?
Right, so so you have this decomposition of the tangent bundle of P into a vertical space, into the vertical distribution plus the horizontal distribution.
Okay.
So for each P and P, so for you get this, right? So you can just take, so you can decompose an element of that uniquely as a vertical vector plus horizontal vector. And then you just project away, you just forget the horizontal part and project the vertical component. And then you use the identification of this with the Lie algebra.
Okay, thanks.
Mm-hmm.
Well, thank you, Jeffrey.
Mm-hmm.
Do people supposed to clap after only the first talk? I guess, I don't know.
It's fine. You can just leave. Yeah, I think I went through my handwritten notes in the wrong order, which is why things were weird. I will be more organized for next time.